Okay, today I'm going to talk about the feedback system, and I covered the first 8 page, 4.2.3, the input noise only, to show you how to handle noise problem. And still in the feedback system and the feedback control system, I'm dealing with how to handle the noise problem. That's the big issue. How to minimize the noise spectra when you try to find the system function, which is H. So frequency response function. Then how to minimize it. So how to find the H with the minimum the noise disturbances, all that kind of the things is what we're going to do. So a feedback system, and we are going to talk about here the negative feedback system. So if it's a positive feedback system, as you saw so far, this is U, okay? This is U. U is equal to X plus, if this is a Z coming in, is X plus Z. But if it's a negative feedback system, it's going to be X minus G. So last Friday, I gave some brief, simple exam problem, and something like a valve along the pipeline. So as it passes the certain pressure, the threshold, certain pressure threshold, the valve could open just instantly, just opens up to relieve the pressure. So that's kind of the negative feedback. So that situations you can, to get the U supposed to be X minus G, and this kind is feedback system in there. And that's the, so this is the Z is going to be H2 times Y, and this is Y, this is also Y, tap in the same line, and of course Y is equal to the H1 times a capital U, okay? And also from this line here, so you have to have the original, the signal X, and the U is of course X minus G, okay? So H1, H2 could be unknown. So X is measurable, Y is measurable. So you have to determine the system parameters H1, H2. Now it's suddenly we have a summer here. 갑자기 여름이 왔어, summer. And I don't see the spring. I saw the winter is keep coming back when summer tried to stay in here. Then now the winter is suddenly gone, and now spring disappeared, just evaporated, and summer is here since yesterday, 27 degrees. It's amazing. No summer, no fall. Winter, and next what? Summer. That's what in US, Chicago, there is no spring at all every year. Winter, the next moment when you get up in the morning, it's whole summer. Okay, Jabam, you're a little bit late today. I announced last Friday. If there's no conflict, I want to give final exam on the 18th of May, which is Wednesday, because the STX students are coming in Monday or Wednesday. So, and 23rd, I'm going away for 2 weeks. So in the final exam, when you take the final, I want to be here. So would you check your schedule? If you can come, then I have to reset the schedule. I think everybody else already know. How's 18th, Wednesday? It's okay? Okay. All understood. All right, so no extraneous noise. Extraneous noise. What does it mean, extraneous? Chusang, what does it mean? No extraneous noise. I used this here. Textbook used this word. It's extraneous, from outside, coming from outside. So no noise coming from outside. But in this diagram, there is no noise in the system. But this is explaining the feedback system, okay? So this is the situation that no noise. The Y, take a look at all here. Y is equal to H1 times capital U. It's all a Fourier transform. T indicate the finite Fourier transform. Okay, eventually it drops everything. And H1U, this U is X, capital U is equal to capital X minus G. Okay, negative feedback system. So G is equal to, this is coming this way, H2 times capital Y. So it's every diagram as I go through, this is the approach I suggested to get the relation between the parameters or among the parameters, and stare at that equations, then you can really solve the problem and get like a system parameters expressed as a function of the measurable x and y. So here is y is equal to I'll just do a little bit more here, then I'll skip it because you can really see it. Y is equal to H1 times U. Y is equal to H1 times U. U is X minus G. G is H2 times Y. That's what all spelled out here. Then after that, still in Fourier transform, you just expand these brackets here. Then you can express the function h as y over x. Y over x from here is h1 over 1 plus h1 times h2. Then I can say this is from this relation y over x. Y over x, you know, this is known, this is known. So this quantity is measurable, and this h, the whole quantity, you can calculate, okay? Because of course x and y are known. Then you can determine h, but h1 and h2 are not measurable. But overall, H is, you can compute that. So, if Z is measurable, in the feedback, negative feedback system, then you can do quite a bit. If Z is measurable, then you can determine the H2, because the Z is H2 times the Y, then you can determine the H2. If you determine the H2, that's the condition that you assume you know the Z. Okay, if you assume you know the Z, then you can determine the H2. Then you, from this relation, you can determine the H1. Okay, so this feedback, the control system here, you can put the non-system. Then you can really prearrange the H2 parameter. Then every parameter in the diagram can be calculated or measured. Measured, remember, is always X and Y, input and output. And noise in the system usually unknown, usually unmeasurable. That's what happened. So that's why you use gamma XY to really see what? The noise contamination in the system. Okay, so that's what the plan is. And see, so here, suppose the H2 in the negative feedback system, if H2 is a preset, the system parameter, then you can determine, as it indicate, H1. You can determine all the H1. Of course, non-value here is C. XX you know, XY you know. This is all measurable quantity. Then preset system parameters, you put that in the system, then you can calculate all parameters. So now inject into the noise into the system. So now put what I said here, noise enters into the feedback system. I just inject the N, noise in the system here, but no noise here. If I put the noise in here, you should be able to solve. Not the big issue. H2 usually not measurable. So it's identical except the N. Well, here in this portion, capital Y or small the Y, lowercase y, is of course the V plus the N, okay? And in this loop is the same. This loop is no difference. But the N and X doesn't have any correlations, vice versa. Y is equal to V plus N. U is equal to X minus Z. Z is H2 times Y is here. This guy is this guy and that guy. This is negative. So if you look through, very systematic. The V here is equal to H1 times the U, capital U, which is, so U is here, you plug back in here, you have this. Then just this algebra. So if you just do the algebraic calculation, then you can determine the expression. Capital Y is a Fourier transform. Y is equal to that times capital X plus 1 over 1 plus H1, H2 times N. noise term. This is input term. Noise term you can separate. So why I just rewrite the last line from previous page. This is what that is. And I call this H1 over 1 plus H1 H2 as a capital H and X plus N. So by looking at this, Y is equal to HX plus N, just write the open loop. This is open loop. From one side, just go straight in and go out. This is open loop. If it's coming back, then that's a closed loop. It's open loop, naturally. So this is Y, and this is N, noise, is right here. And this HX is H times X, okay? Of course, Y, by looking at this portion, Y is equal to the R, output from the system, before getting into the transducer pickup station. The N tilde is right here, is N multiplied by 1 over 1 plus H1 H2. I think here is a mistake. What mistake? This whole thing is called N tilde. I think I corrected it here. Okay? So I corrected in my note. So put the whole thing here is, this is not N, but N tilde, like this. Change that. You know this okay? No. Change that. My note I corrected already. So this is in frequency domain, this is in time domain. So tilde we carried along here. So Y is R plus N tilde. Okay. So this is what the diagram is. So it's right here. So now you visualize a Fourier transform, which gonna be capital Y is equal to capital R plus capital N tilde. Then you pre-multiply X, then you can see this is straight from here. Multiply X, multiply X, multiply X. Then throw into the spectral domain, then you can have GXY, GXR, GXN tilde. N is a noise. It's extraneous noise coming from in the foreign country, so you can delete. It's uncorrelated. Okay? So the process goes identical as I have done always. Then pre-multiply Y, then you have this. Then we know this guy is equal to 1 over 1 plus H1 H2. This is absolute square, because this is G N tilde N tilde, and G N N, remember, that's the parameter absolute square. So this is what happened here. Then GXY comes in XR. This is equal to XR is equal to H X GXX. Is it, by looking at it, is it clear? No one? Clear? Well, if you study a little bit, it should be very clear. Otherwise, GXR, look at this. R. The GXR is equal to H times GXX. Is what this is. And XR is equal to XY. Why? Why this is equal to this? Because noise is uncorrelated noise. So that's why whatever the parameter couples with the N, that's uncorrelated. So from here you have GXY is equal to GXX. H is measurable. Here in this, H is independent of noise. It's measurable. So I know when you look at and study it, you of course you're not just to go through the algebraic relation, but it's kind of a physics-based relation I want you to study. That's far better than algebraic relation. So this is gamma xy square. It's the same way. From the start, from the definitions, using the non-parameters, unknown parameters, you can configure like this. And the G and tilde is n multiplied by, you don't have to remember, 1 over 1 plus H1, H2, way at the top. So expressed as a function of GYY, 1 minus gamma xy square. G and tilde is the calculatable, not measurable, but you can calculate. This you can calculate. Gamma xy square you can calculate. You can measure, I'm sorry, you can measure, you can compute. Okay? Yeah. Look at this. Gamma xy square, measurable? Measurable? Gusto, measurable? Say yes. Anything on xy, measurable. GYY, measurable? 영원, measurable? Yes. Then GRR you can determine, right? 2 parameters you can measure. Then GRR you can compute by 2 measurable. H you can calculate by dividing the measurable over the measurable. GXY measurable, GXX measurable, H you can determine. So you can really look down and try to get understanding. GYY is G. Always get the diagram in your heart where this relationship holds true. Okay? This is with the noise in there, in the output diagram. This is up here. GRR, H is this. Then GNN, you know this from here. GYY. Then before you look at this guy, gamma xy square is GRR over GYY. It didn't suddenly appear. Up there we derive this expression. GRR, we have expression there. GYY, we have expression there. Divide each other. You have this relationship. Gamma xy square coherence function, the noise term is right there. If this noise term, if noise is not there, what's the value of GNN? No noise. What's the value? This, if there is no noise, this term is not there. No noise. Then what's the value? If no noise, this guy over this guy is identical, then that's a 1, then gamma xy squared is equal to 1. What does it mean? No noise in the system, of course. This part you might have to spend some time, maybe look through the relation, how it arrived today. Then tomorrow, after soccer game, you come back, then look through once again. You may not need to go through the review 3 times because all KAIST students are bright students, so you may not need, but be sure spend another hour to look through. Okay, the relations. So now with the negative feedback control system, and there is a slightly more realistic things I put that in, and looks like too complicated, but if you really sit down, look through, turn off TV, then it's going to be very straightforward. Okay? With the TV noise, it's not going to be straight. It's confusing. Look at this. The negative feedback control is here. Okay. Now, after that, 2 things are new here. This area is new, and this is we just did it here. And A is this is somehow when I draw this diagram myself. Nowadays, Higyu is mostly helping me up. But when I draw this one, I think this symbol and the shaker is overlapped, then it's masked. You should write as a shaker, K-E-R. Is there? E-R? Shaker. Yeah. A is like a shaker. And when you hear about the shaker, if you were down there in the lab, when you down there in the lab, you saw the shaker mounted horizontally, right? And it shaker stem goes in and out this way. But that's a very typical one. But another type available, which I use all the time when I was in state, I have 2 different kinds. One is very small, it's stand alone. It's a shaker, you can just pick it up, hold it, small shaker. Another one is a heavy shaker, a little bit big, because it drives the stroke more stroke length, more powerful. The other little one is also for small system, you can put that in. So what I usually do for the shaker, which is made by I think it's about by the one vendor, one company. Oops. Wilkinson. It's nice to know. I was searching before. Wilkinson company makes that freestanding the shaker. It's not like a Ling shaker, they don't do that. Anyway, so that shaker, A is a shaker, standalone shaker, from here up to here. Then there is the wire you can hook up by the two different locations. You can input the force, you can input the acceleration using X, okay? And the shaker has its own characteristics. So A is like a frequency response function. But frequency, then here there is a force transducer or the accelerometer, 가속계나 the force transducer, whatever you call it, is here. So you can measure the A as a freestanding shaker. Or once you attach here, you can measure the U. Got it? As attached on the system, then you have to determine the relevant frequency response. So you have to be kind of careful. So here is A there. W is, think, before you attach the shaker stem to other location. So this case is you screw or bolt it into the structure. In that case, U is equal to A times X. Got it? If this is bolted here, you measured here using the transducer already implemented here usually. But U, capital U is equal to A times capital X. But if you unscrew this, okay, then as just a standalone system, that's gonna call the W here. Got it? Before going into the transducer. Then that situation is a W times AX. Okay. So that's the way. And of course, the H is here, B is here. Usually you mounted this guy right on the structures. Okay, that situation is really U is equal to A times capital X. Okay, so this is what the system. So X is, of course, the signal which goes into the shaker, then that's none. From the function generator in downstairs, okay, the sinusoidal signal that it comes out, that's the usual X. Before it goes into the out. When X sinusoidal signal goes in, then comes out here, if this is attached to here, it's no longer the sine signal. You notice that downstairs when you conduct the testing? It's not nice sinusoidal comes out from the function generator. It passes through the shaker. Then when you really check the transducer output right here, that's not sine. It's kind of a distorted sine because it's already interaction with the other structure. It's all affected. Okay, remember. That's a U. So then this is X is measurable. X is measurable, of course, coming right out from the function generator. It's a shaker. Is a W measurable? Yes, W, you can unscrew this, unscrew this, and X signal comes right in, then it's a free stand. You can hold it, then you can measure the output right here as a W. Not screwed up, not screwed in to other structures, other mechanical component. That's a W. W is measurable. You can unscrew, you can measure it. And U is, of course, really measurable, because this is really coming right out from here. The shaker is attached, screwed into other system. That's measurable. How to measure it? Usually the transducer is already implemented here. Force transducer or accelerometer, 가속계 혹은 force transducer, it's all implemented here. It's measurable. It's A, you could say A is frequency response function for shaker, usually available or not available, because this could be unknown, because this could affect. Because if you want to put U here, capital U is equal to A times X. And H, the system, H and B are unknown, as we saw before. Of course, N is uncorrelated noise, which source is unknown, but we try to minimize it. We try to minimize of the effect of the noise. So that's what things come in. So this is what the system, we're going to look at it. And other relations, as you would see, identical approach we're going to go through. W is before it attach, okay? A times X. V is here is H times H. The V is equal to H times what? This is U right here. So V is equal to H times U. Can you open the door a little bit? Aren't you hot? Feel hot? No? Let's open a little bit. 조금만 열어놔. The Y is equal to the V plus N. Capital V plus capital N. Z is equal to B. Capital Z is equal to B times capital Y in the frequency domain. That's what this is. And U is equal to U is W minus G. Is a negative feedback control right here. After that, you just plug in all the informations right there. From here, plug in. Then simplify it. You move this guy to the other side. Then AX minus N is BN is here. Once you complete up to here, then it's piece of cake. So from here, U is equal to AX minus, it's all relation among the parameters. Then Y is Vn plus N, you can find it. Then you can simplify it. This is identical. You can simplify it. This guy is plus 1 denominator is the same. Numerator is simply n plus nhb is right here. It cancels up. Then you have y is equal to that term, which is x term and n term. Okay, a little bit wake up. It's okay? Okay. So I said computing spectral quantities. Then once we compute all the Fourier transform information in the frequency domain, then now then you are ready to go into the spectral domain. So gxn is equal to 0. I said let. Let means what? Assume. Is it meaningful assumption? It's extraneous noise, uncorrelated noise. Is it good to assume? Yeah, it's just coming from the third world. It's not coming, it's not part of the X, things like that. Then you can set this is equal to 0. Then this will be equal to only xv because n term is out. So this is equal to this. Then as you go through, h can be finally expressed as gxy over gxu. Is u measurable? Yes. gxu measurable? Yes. Then h is of course measurable. This is measurable, this is measurable, then h is measurable. Or, you know, in the dynamic signal, the analyzer, they have a limited number of parameters to display, so otherwise you can compute that. Because you know this, then you know that. You make a division, you can find the h. Have you seen this u is expressed as this? Where? Bottom of the previous page. We derive this expression in the Fourier domain, frequency domain. It's all the Fourier transform. Then pre-multiply x star. What's a star means? Conjugate. Conjugate of x. Okay, pre-multiply. Then now you got this. This is the final expression as a Fourier transform. Then you are ready to throw into spectral domain. Then x star u is gxu. X star x, gxx. This is a g, xn. gxn, 0, because it's uncorrelated. So you have that expression. So the one I'm showing so far is the most complex situation in my note. So if you digest this 100%, for some of you it's nothing. But if you digest this, then you understand what's going on here. So you see here, W without attaching to structure. U is attaching to the structure. U. W, let W be measurable. Then A, you can compute that. So when you solve the problem, you have a lot of time you have to make a meaningful or physically make sensible assumption, not simply assumption. That's what I want you to be careful. That's why I always demand physics of the theory. Otherwise, you have a beautiful theory, then what they do in the research is you start to assume. You develop the total solution. Then you start to assume, then you drop the terms. If you don't be careful, you drop the physically very important terms. That you have to be careful. So you can jeopardize your theory, because at the beginning it's good. The whole thing is all good. Then start to make assumption. Make a meaningful, physically realizable assumption rather than nonsense of assumption. If you don't have that term, it could be a disaster. Of course, it's nice to solve the problem easily, but defeat the purpose. Then assume H and A are known. Then what happened from the equation up there? This equation is okay. Then you can determine the B. Assumption H and A. A is what? Shaker. Shaker, the frequency response function, and this guy is structure, the H. Assume, be careful. Then you can determine B. B is what? Feedback system. Okay? Or, a lot of time, this feedback system characteristic, you can determine prehand before you set it up. Then you can stick them into the system. If that's what's your preference, then B is known from the beginning. Then that's much stable and nicer overall system. But anyway, this relation between the B and the GXX, GXU, and GXY. So GXY, at the, drop the noise term here, this term, this is from the previous page. Okay, this is, so if you drop the noise term, because assume the GXN is equal to 0 as we assume, and GXY is this, so then this is no longer H, because in your system you have a feedback system, feedback control system, which relate to the B. So you have to be kind of careful. Okay, so far all this whole system, how to deal with the system, how to deal with the noise, how to deal with the noise is how much the noise could affect on the system. That's what we discussed it. And from now on, we are going to talk about how to manage the noise, how to get the characteristics of H, frequency response function, how we develop the H function, most optimum H function to minimize the noise spectra. Idea is, hey, noise spectra, don't come up, you stay down there. How to do that? So that kind of the noise management is what I'm going to talk about it, okay? And of course, Wednesday, Friday, I'm going to give a lecture, and it could spill over to Monday. or if I finish on Friday, Monday, I'm going to give you the one of my paper dealing with the random fatigue problem, the random fatigue life on a nuclear reactor problem, which I deal with. So that's what we're going to discuss. Or we'll see how it comes by. But Wednesday next week at 12 noon, I'll give you exam, such a way that you can finish within time. If you cannot finish within 2 hours, something wrong, which I can handle. Okay, you should. I'll make a problem such that you should be able to solve. Don't say, oh, it's too easy, but we'll see after exam how you're doing, okay? And Higyu is going to send you email today for last year's exam, final exam problems. And I'm not, usually my type of the problem set is, a lot of students says some are similar, but similar is similar as long as it's good. Okay? So I'll see you Wednesday. Oops.